All right, 7778. Like, what in the world? Okay, ignore the number 77. This is in chapter 12, Kinetics. But it's about radioactive decay. And on the worksheet, do number calculation number 1, 3, 5, and 6. Where it says the calculation is going to say the radioactive decay law and do 1, 3, 5, 6. Now, at the beginning of the assignment, there's a chart that has a bunch of radioactive chemicals, and it gives you either the decay or the half-life. And for those, if you want to, you don't have to, but you could just fill out the line for U-239, like, and phosphorus 28, uranium 239, phosphorus 28. If they give you the decay constant K, then find the half-life, or if they give you half-life, find the K. That's all you do. You don't have to even do those two if you don't want, because within these problems, you're actually going to do that. So it's not a big deal, and you'll get the full answer key later on anyway. So why am I putting this in here? Okay. I'll put 7778. Well, a long time back, I used to do, actually it's not even 7. In your book, this is in your textbook, radioactive decay is in your textbook, radioactive nuclear chemistry. It's really some neat stuff, but it is not covered on the AP anymore. However, there are some calculations in radioactive decay that are kinetics, and they work just like kinetics. And I just wanted you to try and do a few of these because the way they're worded, it could just be extra practice. I think it'll be good to do problems. So I'm going to go through and just do some calculations. So I'll tell you a little bit about the decay, but in your notes, I have to use my phone here because I'm having out of ink. If you go all the way to near the end of your notes, it says 77 rate of decay for radioactive isotopes. Well, one thing I'll tell you is this. Don't even worry so much about activity, but what that is, radioactivity, whenever a, well, I will show you one of these because it is, I mean, it's worth knowing. Actually, like a U-239, talk about that. Oh, that worksheet. Let me see. I tried to also download the worksheets on here. Let me take a look at that worksheet if it tells you this or not. Yeah, it does. Excuse me. Well, that won't work. Look at where it says on your worksheet, there's a chart that tells you if you have polonium-218 or iron, let me pick another one, beryllium-8. Let me pick that one. That sounds good. Say you have beryllium-8. Now that's interesting because beryllium-8, I would think of that as being not radioactive. Wow. It says it can do alpha decay. Is there another one that can do alpha? Oh, let's do that one. Maybe that's wrong. Maybe it's beryllium-9. But beryllium-8, anyway, what happens is this. Alpha decay means it releases an alpha particle. And when you do nuclear chemistry, you write an isotope, beryllium-8, you put 4, the atomic number on the bottom. Well, on this side, the numbers have to match this side. This is 8, then there should be a 4 right there. What plus what gives you 4? Oh, that's going to be 2 of them. Oh, no. So beryllium can split into 2 helium molecules, which are called an alpha particle. 2 helium molecules with a positive charge. See, if I jumped up to polonium-218, you're not going to have to do this, okay? But it's not a bad idea to be aware of this. I say I would be surprised, because we're going to put this on the AP, but polonium is 209.84. Okay, so this version of polonium is 218. So if it undergoes alpha decay, you take out the alpha particle, it's at 4/2. You've seen that earlier in the year, and 214 over 82. Those add up. And what is 82? It is lead, PB, lead. So what does this mean exactly? If I have a radioactive sample of polonium, just say I have billions and billions and billions of atoms of polonium, okay, or whatever. I won't draw all my billions of circles in there or whatever. Okay, well, what happens is it has a half-life. And let's see what the half-life of that is. Oh boy. I need to have this thing printed out. Polonium-218. I'm looking at the chart on your worksheet. It's 0.23 minutes. So what does that mean? I could have put that into math into seconds. 0.23. 13 or about 13 seconds. So if I had this in 13 seconds is the half-life. It's about 13 seconds, okay? In 13 seconds, half of this is no longer going to be polonium. Half of the polonium atoms are going to turn into lead atoms, okay? Now, they don't have to be on one half of it. It could be scattered throughout. Most likely it would be. So half of these are going to become polonium. Polonium atoms are going to turn into lead atoms, and then helium is going to, alpha particles are going to escape. Those, now, the alpha particles, these radioactive particles coming out, that's what radiation is. It's these particles coming out. And in alpha decay, alpha particles come out. They shoot, the nucleus shoots out helium plus, they're actually helium plus 2 technically, but we don't have to write the charge there. They come out at you. Now, beta particles are like electrons. They can also come out, and they have the formula of 0, -1e. Neutrons can come out also. Protons can come out. Their symbol is 1/1n. So all these different things can come out, radioactivity. And it does it until it becomes stable. Now, what surprised me about the beryllium-8 is that most elements, I think I've told you this before, but for most elements up to calcium, like if I take calcium, the atomic number is 20. Most of them, if you double that number, 20 and 20 gives you 40, then you'll have a stable isotope. That means calcium-40 can last forever, no problem. But now if I have something outside that range, like calcium-42, radioactive. Or if I have calcium-39, radioactive. And what's going to happen when it's radioactive, it will release these particles, alpha or beta or neutrons or whatever, until it forms a stable isotope, okay? A stable form of the other. Now, up to calcium, they need about 1-to-1 ratio. So, in other words, if that's 20, that means you have 20 protons and 20 neutrons. Remember how that works. But when you get above calcium, the heavier elements need a lot more neutrons. So that's probably, that might be fairly stable, or it might also go on in radioactive decay. Now, why am I talking about that? I just want you to have a little bit of a background. Sorry for just a few minutes on that, but we'll get to the math. But all radioactive decay, all of them are first order kinetics. So that means you know how to do the math for them. Even if you haven't done radioactive chemistry or nuclear chemistry, nuclear physics, if you know you haven't done that, you'll know how to do the math. Now, there's one formula. I'm tempted to destroy it in there. Activity. So if you have a Geiger counter is an instrument that you've seen in movies, and they're like, oh, the radiation. They'll put it, like if I put a Geiger counter in front of this, it'll click, and all the clicks happen every time a charged particle hits it. Every time that the alpha particle hits it, it clicks, and it records a number of clicks. And so that's the radioactivity. And if you get a brand new sample, scoop out a radioactive sample, at first the clicks will be really, really high. As time goes by, they'll get lower, 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 lower. Just like reaction rate, exactly like we talked about reaction rate. Okay, but some materials have very long half-lives, like uranium-239. Nope, not uranium-239. That says 23 minutes. Oh my goodness, bad. I was bad a moment ago. I was very bad in my description. I realized polonium, the half-life is not 0.227. It's 3 minutes. I was reading the K value, which I'm going to show you in a minute. I'm sorry for talking about all this. Radioactivity is equal to K times the number of, I'll just show you this. The activity is equal to K, so you got to know the rate constant times N. Capital N is the number of nuclei. No, it's actually the number of nuclei. Nuclei. Well, how about this? Look at easier. The number of atoms. If I know how many atoms are in the sample to start off with, 10 grams of uranium. Tell me how many atoms of uranium I've got. You can figure that out. How many atoms of uranium? And here I'll put the K value for uranium, and that will tell me the activity when I multiply them. We don't have to even do that. I just want to throw it in there because I feel like, oh gosh, why am I talking so long about problems you don't need? Well, because here, I just wanted to show you that. I'll try to write the notes. If you want to, you can skip to 10 minutes. I'm almost at 10 minutes now, and now I'll do the math. Okay, so radioactive decay law. Um, it's called the radioactive decay law, but actually what it is the first order equation. And I have to, again, my notes are not working. I have to go to my, oh boy. I have to go to my phone. I say my notes are not working. My printer's not working, so I couldn't print them because I even read on my own notes as well. Do this. Okay, we give this thing on 7.8 called the radioactive decay law. Looks like that. Oh no, does that screen show up? Oh, there it is. 7.8. But we don't really need that. That just comes from the radioactive law that we'll show you. From the rate law that we'll show you. It's first order. So remember, natural log of the concentration of A final is equal to negative KT plus the natural log of concentration of A initial. So what I'm going to do, now here's a little bit more about this. I can put in molarity and molarity. I can put in the number of moles here and number of moles there. I can also put in, for radioactive decay problems, how many grams of, like, for example, polonium 218 did I have to start off with initially, and then in the end, how many atoms or grams did I have? How many grams did I have here? How many grams did I have at the end? Okay, and the other grams will have been converted over into the other substance. So you can actually do it that way. So I'll do letter, let me see, yeah, A is a good one to do. Now, if you wanted to, you can imagine this as being molarity, because that's how you're probably going to see it. It could also be partial pressure of gases. So I think most likely, if you see us on AP, it's going to be molarity. Molarity, or maybe gas pressure. I don't think they'll put grams. Only in radioactive decay they would. But okay, so letter A says, a 45-gram sample of carbon-11 is measured for an experiment. How many grams of carbon-11 will remain in 55 minutes? The half-life is 20.3 minutes. Now, if I know the half-life is 20.3 minutes, one of the first things I should do is K is 0.693 over half-life. Okay? Or half-life is 0.693 over K. In fact, they're both true. I think that's really the way, this is the way it is on the AP sheet. 0.693 over K is the half-life. All right? I think that's still on your sheet for Chem or AP Chem College Board. But now you can flip those two. K equals 0.693 over T1 half. So 0.693 divided by 20.3 equals, let's see, 0.0341, and it will be now, minute, so it'd be minute -1. Okay, minute -1. All right, so now I know the K value, so I can use this equation to find out how many grams of carbon-11 will there be in 55 minutes. So I'm going to have to find out if you, again, even though it said 55 grams to start off with, no, I'm sorry, 45 grams, you can pretend it was 45 molar if you want to put it in there. So we'll find the final amount of A. I know negative K is 0.0341. The time is going to be 55 minutes. So you see, this is not really too much different than what you saw in earlier problems. Natural log of, now the original number was 45.0. Just make sure you know, initially you had 45.0. How much do you have finally? Now there'll be a little bit more interesting math here. I'll show you. The natural log of A final is equal to 0.0341 times 55 is 1.876. I'll tell you about why I'm putting one more sig fig in a later chapter. Oh, it's negative. Negative 1.8. Is that right? 0.0341 times 55 equals, yeah, negative 0.1876 plus, and let's get the natural log of 45. It's going to be 3.807. Now, what I'll do, combine these two. I don't need my calculator. I mean my phone. 1.876 combined with 3.807 is 1.931 equals natural log of A. Okay? So, to get rid of natural log, what you get to do is you raise E. E raised to the natural log of A power is equal to E raised to that. And when it's negative, by the way, I don't want to, isn't it? Oh no, it's positive now, because that was a negative, that's a greater number. Okay, positive. So, that cancels out this. I'm sorry, that doesn't cancel out that. This cancels out the Ln, and so now A, the final grams or final molarity, if you want to call it molarity, is equal to E raised to that power. So, on your calculator, if you look up here, I've got the Ln button, but above it, it says E to the x. So remember, like you've done this in a math class, and we'll be doing it in here later, log, if you push log, you get a number. If you push shift log, it's 10 to the x. So log measures 10 to what power is equal to that number. Well, natural log means E raised to what power equals that number. So if you have natural log, you push that button. To undo natural log, push shift Ln, which is E to the x, which we're doing here. So E to the 1.93. So I have to put, on my calculator, I type in 1.931, then shift Ln, and that gives me E to the x by pushing the Ln button. And there it is. And it says 6.90 pretty much. You could put 896 if you want to, but I'll put 6.90. 6.90, well, I guess technically I will put the whole number, 6.896. So what does this mean? You started the experiment with 45 grams of carbon-11, but at the end of the experiment, you only had 6.896 grams of carbon-11. That was your final there. Is that all they asked in that question? Yeah. How much will remain? Now, here's another thing I was kind of want to bring up, because this can also just be something that could help you. Whenever you find out the amount that remained, so 6.896 grams remain, but how much disappeared? Okay, just subtract that number. 45 minus 6.896 equals 3.8 with 6. 3.8 grams of carbon-11 decayed. So 3.8 grams decayed. Now, they didn't ask for that in the question. This is what remains after that 55 minutes, but that's how much decayed. Sometimes in kinetics problems, they'll have you do a calculation, and they'll ask, well, what amount did you start off with, and what amount remains? All right. Now, B, well, what fraction will remain in 12 minutes? Don't worry about B. You don't have to worry about B in this particular form. But I'll tell you this. Actually, I just found the number on there. But if they want to know what fraction was remaining, like if I had just done it on the problem number 1, you take the amount remaining, 6.8? I can't remember, about 6.8 or something like that. I can't remember. And you would divide that by the original amount that you had, which was 55. Okay? I can't remember my number, and I just erased it. Can I see it up there anywhere? 6.80896, something like that. 6.896, something like that. You would take that amount, final amount, divided by, oh no, it says calculate the fraction remaining. Yeah, no, that's right. It'd be your answer to the last problem, divided by 45 grams. And that would give you a fraction, not a percent. To get a percent, you do times 100. Okay, but I'll skip to a percent problem. All right. Here's one that says, how long would it take for a sample of strontium-90 to decay to only 20.5% of its original amount? Okay, so strontium-90 has a half-life 28 years. How about that? So we'll do the same thing. K will be 0.693 divided by 28 years, which is, now if you wanted to use the longer equation, you could. You don't have to use this half-life equation, but it's much easier to do this. 0.693 divided by 28. 0.0248. and it's year -1. Wow, year. So how long in years will it take for strontium-90 to decay to only 25% of its original amount? All right, so what's going to happen is this. Look at this equation, and what we're going to do is, we weren't given any amounts, and they could ask you this with molarity again. It could just be a molarity, pretend it's a molarity problem, and they said, how long will it take for this chemical, this reaction to occur, for 20.5% of this reactant to decay? How long will it take? Okay, your original amount, just let it be 100, like 100%. Let your original be 100, and let your final be 100 minus 20.5. Because your final amount, if 20.5%, oh no, I'm reading it wrong. You got to read these questions carefully. If 20.5% of its original amount, okay, that's not true. So that is the part remaining, Ln of 20.5. All right, so it goes down to 20.5. You start at the beginning, you had 100%. At the end, you have 20.5%. So this is what I was telling you before to think about. 100 minus 20.5, 79.5% decays or reacts. So if you heard those terms, if I had said another way to do the same problem, I could have said, you've got this strontium, in this reaction, 79.5% of the strontium reacts, okay? Then it could be, how long will it take for 79.5% of it to react, okay, or decay? How long will it take? So in the beginning, you had 100%, 79.5 went away, in the end, you had 20.5%. It's just a good thing with these percentages, and I had it for grams and the other, to be up, think in your mind, this is your original amount, this is your final amount, and that's the percent or the amount that decayed, that went away. All right. Well, anyway, all right. So the natural log of 20.5 is equal to, here's my K value, 0.0248 year -1 times the time, and we don't know the time, we're trying to find out what is T, all right, plus natural log of 100. Okay, so I'll do the math here. So 20.5, the natural log is 3.020. What I'm doing in sig figs, if this has 3 sig figs, I'm putting 3 after the decimal. And we'll talk about why we do that in a couple of chapters when we get to acids and bases and log and pH. It's a rule involving logarithms that you use. All right, that's 0.0248t, but I'm not going to worry about it in this chapter. I'm sorry, plus, and the natural log of 100, and that should be an easy, oh no, but this is not log, natural log, sorry. It's not easy. I'm about to say 10 to the, never mind, it's not 2. Okay, 4.605 will be that number there. Okay, now, oh, and by the way, that's, in my equation, that's negative. I don't want to mess myself up. Oh boy. Negative 2.048t equals that. So now I'll subtract 4.605 from both sides. 3.020 minus 4.605 gives you negative 1.585 equals negative 0.0248t. Divide both by negative 0.0248. And the time it takes is 1.585 divided by negative 0.0248, 63.9. 60, well, I'll put it here. 63, actually 0.91 if you want to go. Oh no, that only has 3 sig figs. 63.9, and what was the unit? Years is equal to the time. So I just wanted to show you a little bit of how the math works on those. And you'll do problems like this on your thing. Now again, I'm putting in percent. It doesn't really matter. I know the amount in the beginning and the amount in the end. I can put in molarity, and that's what you'll always use, molarities. They could give you pressure. If you ever had pressures, you wouldn't call that a molarity. You might just put parentheses there, but the same law. Pressures or molarity is probably what only thing you're going to see in this But you could put initial grams, final grams. You could put initial percent, final percent. Okay. All right. Now, that was letter C. Letter D, I won't do letter D because it's like the one I showed you. It just says, how long will it take for 74% of a sample to decay? So how long will it take for 74% to decay of phosphorus? So what they're saying is, think about that. You start with 100%. Your initial amount will be 100 if you do it. If 74% decays, then that means 26 remains, right? 74 decays, so 64 remains. You just say 100 minus 74. So you put here the original amount and the remaining amount here, remain, on these problems for the homework. Now you could see that pop up, in another form. Again, you might think, well, why are we doing it? I'm just showing you other ways they can word problems. This is more like something that on the AP, it's like, we'll get you a 4 or a 5. Like say if they did a problem and they said, oh, this reaction you've gone through, you found rate equals, you found K, you found the units and all that, you're done, you get to the bottom, and they'll say, how long will it take for 83% of this to decay? Or to react? How long will it take for all the original sample to react by 83%? You don't even have to put in the molarities. You can put in, you start with 100%, and then if, well, let's make it easier. I said 74%. 74% away, so you had 26 there. All right. And you know what? That's the end of it. That's all of it. That's the whole thing. That's all I wanted to show you. So, every problem, I just wanted to show you a little bit, dealing with the E and all that stuff. There is one where you go backwards, isn't there? Have you find? What would that be? Well, I think it's popped up in some other. I'm not going to try and I'm already. This whole thing is kind of just possible anyway. I want to get in there. All right. So just work those problems I told you, number 1, 3, 5, and 6 there that are on the paper. None of those should be find the activity. We're skipping those problems. Yeah, they're in the first part. You're not doing that section. You're going to where it says radioactive decay law and doing those 4 calcs. All right, I'll see you.